Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in last video we finished the module 2. Now in this video we will see the module 3 problems. Okay. So first is based on the problems on independent elastic constant. Means with the different condition, how many independent elastics are that constants are there for that particular condition. So that we will see in this one. Okay, and this question you can find in your question bank also is there. So just see the question. Write the number of independent elastic constant for 3-dimensional anisotropic. So here is the given condition for whom you have to write the independent elastic constant. Anisotropic, monoclinic, orthotropic, transversely isotropic, and isotropic. So for these 5 conditions you have to write the elastic constant. How many elastic constant are there? Okay, so let's see the solution. So first is for an anisotropic material. So for an anisotropic material, what are the constant? So let's see here. A material is said to be anisotropic if it has different properties in each direction. Means in each direction, this should have the different property. Right? Means if suppose they are like in this direction we are seeing. So whatever the property in this direction we will check. Just like ductility, matter or anything or arrangement. Then that same should not be in this direction or same should not be in this direction. Means in each direction, the property should be different. Okay. There are 21 independent elastic constants required to define the stress-strain relationship for anisotropic materials. How they are connected. Just see the relationship between stress and strain. So how they are connected or how they are related. Right. For that 21 independent elastic means it should not depend on the other. Each elastic constant should be independent from the other elastic constant. So total 21 independent elastic constant is required. Then only we can define or we can find the relationship for an isotropic material. Okay. Next is an isotropic material is defined orthotropic when shows property that differs along 3 mutually orthogonal 2 folded axes of rotational symmetry. So now just see the same an isotropic becomes orthotropic, right? In that case, what happened? Out of 21, 3 differ that differs along 3 mutually orthogonal. So means like x, y, z are mutually perpendicular. So that same here 3 mutually orthogonal that should have different. Then if you will fold the axis in that folded axis, 2 of the rotational symmetry means along the after folding along the 2 axes it should have the symmetry of rotation. Then the anisotropic becomes the orthotropic. So this condition is important. Like they can ask, write the condition of that elastic constant when orthotropic becomes the anisotropic or when anisotropic becomes the orthotropic. That condition. So this condition is very important. 3 mutually orthogonal and 2 folded axes of rotational symmetry. Means 2 folded axes of symmetry for rotation. So these conditions is once these 2 conditions will fulfill, now anisotropic becomes orthotropic. Okay. So next is for monoclinic. Right. That are also the type of this one. So if a linearly elastic solid has one plane of material symmetry, one plane, either x, y or z, in any one plane of symmetry is there, it is called that's why it's a name, plane. One is mono. Their name is monoclinic. For such a material, there are 13 independent elastic coefficients are there. Right. So for anisotropic, 21 independent, and here 13 independent elastic constants. Remaining 8 can depend on the others also, but 13 should be the independent elastic coefficient. Okay. That is for monoclinic. Now orthotropic. So let's see. A material is said to be orthotropic if it has 3 different properties in 3 mutually perpendicular directions. Means in x direction they have some other property. In y direction that having some other property. In that direction also they have the different properties. In each direction it's not like that like x, y and z is there. Here whatever the property will be there in this direction, that property won't be same. That property will change. And in this direction also that property will change. So in orthotropic, it has three different property in three mutually perpendicular directions. So having in this different property here also means along the x-axis different property, along the y-axis different, and along the z-axis also they have the different properties. In that case, that we can say that as orthotropic. Already we had seen in isentropic, what is there? That three orthogonal, not only the mutual perpendicular, three orthogonal property should be different, and two, that fold of symmetry, that axial rotation should be same. Then only we can say that is orthotropic. So in this case, three are already same. So now just see here. In this case, how many are there? 13 independent. Earlier, how many was there? That 21. So now 13 independent elasticity. Now in case of orthotropic, only the 9 independent elastic constants are there. So there are 9 independent elastic constants required to define the stress-strain relationship for orthotropic material. So for orthotropic material, 9 should be independent, remaining 12 should be dependent, right, to each other or anyone. That means it should be dependent. It's not totally independent, but 9 should be totally dependent, or you can say remaining all are 0 also. Now next is isotropic. That was anisotropic. Now this is isotropic. A material is said to be isotropic if it has similar property in each direction. So whatever the direction is there, in the each direction they will have the similar property, right? If you will go for the x-axis, they will have the similar property. Y-axis will have the similar property. Z-axis also will have the similar property. Okay. The relationship between various elastic constant is given as E equals to 2G into 1 plus U, okay, equals to 3 into, so just see here how E is related. So E is equals to 2G into 1 plus U, and also E is equals to, this is in terms of G, now this is in terms of K, 3K into 1 minus 2U, right? So this is the relationship between what? Various elastic constant. Okay. So now from these two, what we can write? That E equals to 2G into 1 plus U, that is also equals to what? 3K, means what? This will be equals to this one because left side is equal, hence right side also will be equal. So E equals to 2G into 1 plus U equals to 3K into 1 minus 2U, and that relation is here. So that is for the anisotropic process. Sorry, isotropic process. Anisotropic, this is not there. For anisotropic 21, that constant is there. As seen in the above equation, there are total 4 elastic constants. So in this case, only the 4 elastic constant is required. Okay, I'll just see how you will. After multiplying 2G plus 2GU, and here 3K, so 3K minus 3 to the 6KU. So 6 minus 6 plus 4. So that is only 4 elastic constant is required here. Okay, if we know 2 of them, then we can find the other constant also. So out of these, if we will know the 2, then other constant also we can find. There are 2 independent elastic constants required to define the stress-strain relationship for an isotropic material. So total 4 are there, but if we know the 2, then remaining 2 we can find. Hence, that what is our minimum requirement? That we should know the 2. So that is here. There are 2 independent elastic constants required to define the stress-strain relationship for an isotropic material. Okay. Now next is transversely isotropic. Transversely. Let's see here. The transverse, it should be isotropic, but transverse type. So for a transversely isotropic material, there is an axis of material symmetry. Then just the axis of material symmetry means the one axis will be there. Along that, the material will be symmetrically distributed. Defined as a direction with respect to which the material has identical property. That is how it's defined. So just see, direction with respect to which material has identical property. So which material having that identical property, along that the direction will be there. In addition to 3 planes of symmetry. So just see here, just read here. For a transversely isotropic material, there is an axis of material symmetry in addition to 3 plane of symmetry. So 3 plane of symmetry should be there, and the 4th one is what? Axis of material symmetry also. So when 3 axis of symmetry was there, then how many elastic constant? 4, right? So now So here a transversely isotropic material has, therefore any two material fiber having symmetrical position with respect to axis of symmetry have the same stiffness. Means what if any two material fiber is there and they have symmetrical with that position with respect to axis. So means wherever it is there, that axis of symmetry have the same stiffness. Means what? Like this is there. Any axis is there. Any two material fiber having symmetrical position. So now from here just see. Along this axis, if something is here with respect to axis of symmetry. So this is the axis of symmetry here. So means like this also should be here. Have the same stiffness. Now in this case also if this is there, whatever the other material is there, that doesn't matter. If they have what? Axis of symmetry, right? That symmetrical position with respect to axis, then we can say these two have the same stiffness. A transversely isotropic material has 5 independent elastic constant and 12 non-zero terms. Means total 17 will be there and remaining 4 will be what? 0 term. So transversely isotropic material have how many? 5 independent elastic and 12 non-zero terms. So 5 elastic constant and 12 non-zero term. Okay. So let's see once again quickly. The question is write the number of independent elastic constant. Right. So independent, it should not depend. That's why we wrote that only how many independents are there. If others are dependent, then no need to write. So for a 3-dimensional, for 2-dimensional it will be different. Then we cannot consider the z direction. So whatever is there along that only we have to take. So 3-dimensional for what? For anisotropic, monoclinic, orthotropic, transversely isotropic and isotropic. For these conditions we have to find what? How many number of free elastic or independent elastic constants are there. Okay. So first was anisotropic. In that what was there? How many? There are 21 independent elastic constant. Okay. And what happened in each place wherever it is there that have the different properties. So a material is said to be anisotropic if it has different property in each direction. So whatever direction you will consider, they will have the different properties, right? So then we can say that is an isotropic material. So in that case, what happened? 21 independent elastic constants are there, right? To define the relationship between an isotropic material. Means if anisotropic to anisotropic material is there, how they are related, or in between that stress-strain relationship, right? So total 21 independent relation should be there. Then only we can find the relation of an isotropic material, not relation between, relationship of stress-strain for that particular anisotropic material. We cannot combine, or we cannot find the relationship between two anisotropic material. How stress-strain is connected? Just like what? Like stress is directly proportional to strain. Here we can say that this directly, right? So how this only is dependent, like whatever the new proportionality constant will take, stress is equals to what? E into strain, right? So now how this proportionality constant will affect or will be there, that only defined here. So total in case of an isotropic, 21 independent elastic constant should be there. Next, an isotropic material is defined orthotropic. Now when an isotropic becomes orthotropic, that already we have seen how many? 3 mutually orthogonal, or like along x-axis, y-axis, z-axis, the property should have different. That means they should have different property along the x-axis, y-axis, z-axis, or mutually perpendicular or mutually orthogonal axis. And 2-folded axis of rotation of symmetry, means 2-folded, where it can rotate in that folded axis of symmetry. That 2 axis of symmetry should be there. Then that anisotropic becomes isotropic. Next, for monoclinic, how many it's required? Total 13 independent elasticity. Why? Because one plane of symmetry is there. So now in case of monoclinic, okay, monoclinic, that elastic solid have one plane of symmetry. So then it is called, because of one plane, it is called as monoclinic material and having 13 independent elastic coefficient or elasticity coefficient. Next was orthotropic. So just now we are seeing here that orthotropic. So in orthotropic, what? Three should be mutually perpendicular, and along the direction it should be different. A material is said to be orthotropic if it has three different properties in three mutually perpendicular directions. Means along x direction the property should be different, along the y direction the property should be different. Means it should not match to x direction. Along the z direction the property should not match to x and y direction. Similarly, for x direction the property should not match with y and z direction. Means with the mutually perpendicular it should not match any property. Similarly, for y it should not match with z and x axis property. Okay, so an isotropic becomes anisotropic becomes orthotropic, or simply if an isotropic is not there, then directly you can define for the orthotropic. Means along the axis the property should be different. They should not coincide or have dependency. There are 9 independent elastic constants required to define the stress-strain relationship for orthotropic. So here in this case, total 9 is required. The next was isotropic, right? So isotropic means what? Had similar property in each direction. Like in x direction, whatever the property is there, the same should be in y direction also and in z direction also. So a material is said to be isotropic if it has similar property in each direction. So means whatever the property they have in x direction, that should be similar to y direction and z direction also. Similarly, for y direction, if it is whatever the property is there, that should be similar to x and z. Similarly, for z also. Now, the relationship is what? That between various elastic constant is E equals to 2g into 1 plus u. That is in terms of g. In terms of k, that is equals to 3k into 1 minus 2u. Now, if you will solve this one, then what we will get? As in the above equation, there are total 4 elastic constants. Right, so let's see here. Just expand this one because these two are equal. So 2g into 1 plus u is equals to 3k into 1 minus 2u. Let's multiply 2g into 1. So 2g plus 2g u. Okay, that is equals to 3k minus 6u. 6k u. So just keep this to the side. Right. So from here you can see that 2u this side and 6u this side. So how many total difference will be there? That 4 elastic constant difference will be there. So in that total 4 elastic constants are there. That independent elastic constant, because here we are dealing with independent elastic constant. Now 4 is there. If we know from 4, that out of 4, if we know 2, the remaining 2 we can find, and then we can find the relationship between stress and strain. Okay, for the isotropic material. So here only we required 2. Once we know the 2, remaining 2 we can find. But total it should be that a total it is 4 elastic coefficient, right? That elastic constant. Now in case of transverse, what was there? For the here an axis of material symmetry, right? In addition to 3 plane symmetry. So whatever the 3 plane symmetry is there, that will be there, and as well as what happened? Axis of material symmetry. Material means along that axis material should be same. Then material of symmetry is there. True. Okay. Therefore, any 2 material fiber have symmetrical position. So whatever, if you will consider the 2 different fiber, 2 fiber material, then they will have symmetrical position. Then we can say that is transversely isotropic fiber. Position with respect to the axis of symmetry have the same stiffness. Means if they have the same stiffness, they will have the symmetrical position. That means material fiber at the symmetrical position that will be there. Then only they will have the same stiffness. Next is a transversely isotropic material has 5 independent elastic constant and 12 non-zero. So 12 non-zero means what? Then definitely it will be dependent. So 12 will be dependent. Only the 5 are independent elastic constant. So this you can just refer the okay, actually this is one only. Transversely isotropic material and overview. From where you will get that science direct. So actually this is here that space. This is continuous of this one. This is not there. So this, just remove this one and then you can search. You will get this topic there. Okay. So if you have any doubt regarding this, you can just comment on the video or you can contact me regarding your doubts. I will clarify that doubts. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.